Welcome to Lab 2, where I explored the motion of an object falling towards Earth. In this lab, I dropped a tennis ball to examine its motion as it moved towards Earth's surface at changing velocity. The importance of this examination was to be able to explain why situations like this occur, by applying Newton's second law and its relationship to net forces. To do this, I compared the observed values of displacement in the y direction to theoretical models with the force of gravity with and without the drag force. In this lab, I first videotaped an object being dropped. I uploaded this video to Tracker where I plotted its displacement during the time of the video. I then created computational models that I compared the observed model to. In this experiment, the fundamental principle used to analyze the object's changing velocity was Newton's second law. This principle was used because it relates changing velocity to the forces acting on the object, which is what this experiment aimed to understand. Precisely, Newton's second law was applied to understand that because the object had changing velocity, the net force acting on the object could not be equal to zero. This is seen in Newton's second law equation, where the net force acting on an object is equal to the product of mass and acceleration, where acceleration is a relationship between the object's change in velocity over time. Even on a simple velocity time graph, it is seen that changing velocity correlates to a non-zero acceleration, which is the result of a non-zero net force. Some of the forces accounting for this non-zero net force include the gravity force, which is the product of an object's mass and the gravitational constant. It acts by pulling the tennis ball towards the Earth's surface because it attracts two objects of mass. Another force is the drag force, which is a force that is opposite to the tennis ball's motion. We can calculate this using the equation b times velocity squared, where b is a proportionality constant that depends on the properties of the object. Finally, in this lab, I will begin exploring the concept of terminal velocity, which is the point where an object is no longer accelerating because the forces acting on it cancel each other. This is illustrated in Newton's second law, where constant velocity correlates to a net force of zero. Here is a video of my tracker setup where the ball is the reference point, starting at the origin before moving in the negative y direction. Additionally, as represented by the data points which become increasingly further apart, we can see that the ball is experiencing changing velocity. Next, I edited coding so that the theoretical movement of the tennis ball could be modeled. Firstly, I changed the initial conditions such as mass, position, and velocity. The position and velocity vectors were taken from Tracker. The velocity vector is 0 because the object started at rest, so there was no displacement during the first two recorded points. Next, the gravitational constant 9.8 meters per second squared and object's direction of movement, j hat, in the y direction were included so they could be used in the following gravity force formula. This formula was used to update the net force as the object moved because no other forces were being evaluated at the time. The calculated net force from the force of gravity equation was used in Newton's second law to calculate the changing velocity and position. These calculations continued to be calculated until the end of the video as coded for by a while statement that continued until the last time frame at 0.6 seconds. This is the resulting computer model. Following this, another program was edited with all the same properties except this one updated net force to include the force of draft. This was done by including the draft force equation with an estimated b value based on similarities between the final positions of the observed and modeled object. This is the resulting computer model where the orange arrow represents the force of gravity and the light blue arrow represents the drag force. Here we have a graph that compares the observed motion to the modeled with gravity and the modeled with gravity and drag force. A notable similarity between all three curves is a quadratic shape. This similarity shows that in all three situations, the objects were experiencing changing velocity. This is explained in the fundamental principle where non-zero net forces result in changing velocity. However, as you can see, the model position with just the gravity force overpredicts the observed motion, which shows that there are other forces acting on the object. This is explained by the fundamental principle where the sum of the forces, also known as net force, directly affects the motion of the object. Thus, in the model, with a more accurate net force by including drag force, has a more similar motion to the observed object. The discrepancies between the observed and modeled curves could be due to errors in picking the centers of the ball. Additionally, it is evident that video of the observed object was filmed at an angle because I had to rotate the axis in Tracker. Viewing the motion of the object from an angle certainly would affect the analysis of the motion. With this, to improve this comparison of the observed model to the theoretical, I would film the video more straight on. Additionally, possible changes to the model can include factoring in more forces, that is, if they could be identified and calculated. In this lab, the concept of terminal velocity can be explored. Terminal velocity occurs when an object falling towards Earth no longer has a change in velocity because the net force is zero. In our case, this would mean the gravitational and draft forces would cancel each other out, and the position time graph would display a linear line as shown. As you can see, none of my models show this as the velocity is continuously changing as represented by a quadratic shape. However, at the end, the models do appear to begin approaching terminal velocity. Additionally, even if the objects were initially thrown down instead of dropped, the terminal velocity would be the same because the terminal velocity depends on the properties of the objects such as mass, and because the same object would be used, they would have the same terminal velocity. In conclusion, Newton's second law can be used to predict an object's motion that is experiencing changing velocity because it is being acted upon by a net force not equal to zero. In this experiment, the modeled effects of the forces gravity and drag on an object's motion were examined. In doing so, I found that the model that included both gravity and drag were better than the model with just gravity, because it simulated the conditions of the observed object more accurately.